we've got this idea of wave equations and the Balmer series, photon energy, the photoelectric effect, and it's all happening at the same time. Anyway, so there's a bunch of info blurbs here. You can read the history on these things. These are just people's personal lives and stuff. And if you look at the dates in particular, I wanted you to get the idea that a lot of these things are being figured out in the mid 1800s to late 1800s. And so, like, we're going to continue to call this modern physics, but only just because it happened within the past 4 human generations. Okay? So this is the emission of electrons. When we talk about the photoelectric effect, we're talking about the emission of electrons from matter when the matter is illuminated. So that idea, the photoelectric effect, you can even see embedded in that compound word that photons are causing an electric effect. Okay, so you shine light on stuff and stuff happens. But what's the stuff that we're shining the light on? I have this device here, and this is a device I'm going to treat it as a model of the device that we're talking about. I've got a piece of metal at one end. You can see the piece of metal encased inside of this vacuum tube at one end. And then at the other end, I have an electrode. And of course, it's all encased within glass. And the idea is that you're supposed to be able to hold it up on a stand at this end. And I have a wooden stand in the cupboard that I'm not going to bother putting under the camera. But it holds this thing up. And if I shine light on this metal at one end, and I shine it in the right way with the right light, it'll knock electrons off this end. And those electrons will bridge the gap, and they'll fire across the gap, and they'll end up at this electrode. And you can see there's like a metal hook at this end and a metal hook at this end. And so that can get connected with alligator clips to a circuit. That all sound good? All right, so the photoelectric effect. And I've got different versions of this kicking around because this is an old school with old equipment. The annoying thing is that at some point, all of the glass tubes have cracked on them, so the metals become oxidized. So it just doesn't work anymore, which is kind of like annoying, right? But still, I got it as a model so we can at least see the physical thing that I'm talking about, because I can't buy these things out of the physics catalog anymore. That's just not in the budget. All right, so nice thing about an old school is we have the artifacts. All right, so by certain types of electromagnetic radiation. So it's got to be just right. Electromagnetic radiation, of course, falls into categories like radio waves, microwaves, visible light, all that stuff, right? So anything that's electromagnetic radiation is on the table here. But it's got to be the right electromagnetic radiation. So it was first observed by this fellow, and you've probably heard of him. Oops. Oh, man. I just spelled his first name wrong. First name's Heinrich. And if you don't recognize him by his first name, I'm sure you'll recognize him by his last name, Heinrich Hertz. So this must have something to do with frequency. You can guess. 1887. So the effect occurs when metals are illuminated by UV light. Now, UV light, if you recall, if I'm talking about the spectrum of colors, the shorter the frequency, the higher the wavelength. Sorry, the shorter the higher the frequency, the shorter the wavelength. I said it right that time. The higher the frequency, the shorter the wavelength. This is, high frequency. This is low frequency. And if we called somewhere between here and here, the frequency band that we could see, the visible spectrum, UV is anything higher frequency than what we can see, okay, in terms of the electromagnetic spectrum. So when we say that this happens for UV light, we talk about this stuff that's towards the high end of what we can see and beyond. And this is the high energy stuff. One thing that we know about light is that the higher the frequency is, the higher the energy, which is why we use UV protection to not get skin cancer from the sun. Nobody ever wears infrared protection to keep themselves from having skin cancer. UV is the energetic stuff. Okay, so when we say that UV light is going to cause this effect, we mean energetic light. Okay, the high frequency stuff, like this, towards the high end of our perceptive range and beyond. Anyway, so this UV light and can occur with alkali metals. Oh, chemistry. for visible light. Okay, so we need to know about what an alkali metal is. And so hopefully you guys remember where they are on the periodic table. Is it on the far left or the far right? Left, yeah. Far left. And people that are into electronegativity, do they have a strong hold on their electrons or a weak hold on their electrons? It's weakish, yeah, weakish, but not like the weakest. But they seem to be able to let go of their electrons not so badly. Anyway, the electromagnetic radiation releases electrons from the surface of the metal. And these electrons, I mean, it's not even not that complicated when you think about it. These electrons are attracted to the cathode and complete a circuit allowing a current to flow. Well, what's a cathode? One thing I remember from my early days as a physics and chemistry person is that we have ions. And a cation is a positive ion, and an anion reminds me of an onion, anion, and an anion is negative. Cats are positive, okay? So cations, positive. And so anytime I hear something like a cathode or an anode, I know that a cathode is going to be a positively charged metal piece. An anode is going to be a negatively charged metal piece. Cation, anion. Reminds me of the chemistry stuff that I learned when I was a little kid. And by little kid, I mean like your age, right? Like now that I'm old and more worldly. Anyway, so this radiation is going to get sent from a light source. I'm going to draw it in as wiggly waves getting shone in from a flashlight. And as that light hits the metal plate that we're talking about, take a look at this power source. I'll zoom right in so that you can't hardly miss it. This power source looks to me like a basic battery cartoon. It's got a negative terminal. It's got a positive terminal. The negative terminal is connected to this metal plate, which means that this metal plate has an excess of electrons on it. It's negatively charged. And so when I radiate that metal plate, I'm going to send energy at that plate. I'm going to knock electrons off of that plate. And then those electrons, zap, zap, are going to go across the gap from the negative anode to the positive cathode. All sound good? Negatives attract to positives. This reminds me of some stuff that we did earlier with field theory type stuff, right? All right, so that's the story on this little diagram. I'll even label the positive one the cathode. Okay, so the electrons are zipping across that open gap. And remember, I whipped out my model because I got this cartoon here, but this is my old janky one. There we go. There's the metal plate, right? And we scan across the glass gap, and there's my cathode over on that side. Okay, electrons would beam across the gap. Now this guy is supposed to be a vacuum inside, so the electrons should be free to like fly through the vacuum. You know, good sales pitch. All right, so that would complete the circuit, and it would allow electrons to flow freely. Now, if I connect an ammeter to this circuit, of course, ammeters measure the rate of the flow. The ammeter then reads the current. It would be flowing in this photoelectric circuit. And the potential difference, we've talked about potential difference already in the field theory portion of the course. Potential difference, the voltage, across the tube measures the maximum kinetic energy. Remember we talked about acceleration plates? Measures the maximum kinetic energy of the so-called photoelectron. And it's called a photoelectron because it's an electron that was caused to blast off from a metal by getting smacked by a photon. So a photoelectron. It's not like it's a new particle or anything. It's just an electron that got smacked out of place by a photon. Okay? So this photoelectron, its energy, we usually don't measure it in joules. This is weird. This is a new unit. We measured it in electron volts. And so there's this new unit. It's actually like a scaled unit. You know how we use kilowatt hours for energy with household equipment? And that's a bigger unit, so we don't get sticker shock from our electrical bill. We use electron volts when we're talking about the energy of an individual electron to scale it down to a much smaller scale. So electron volts is something that's used as an energy unit when we're talking about real small things like individual charged particles that are flying through space. Anyway, as we shine light on this thing, actually, you know what? Maybe we should make sure we get this definition because I said it out loud, but let's just put it in writing so nobody ever thinks that a photoelectron is its own like new and exotic particle. It's an electron that was removed from a metal atom by shining light on it. Okay, so just so that we don't think that a photoelectron is a new and marvelous thing, although it's a new and marvelous idea, as this thing gets knocked off, we say, the intensity of the light that you shine at that metal, we call it I, it happens to be proportional to the square of the amplitude. And people that are in functions class and talking about waves in their functions notation know what amplitude is when they're looking at a sine wave. But those of us that don't, just in case, here's an amplitude. And so what we're saying is that the intensity of the light, or the intensity of the photo emission, the photoelectric emission, the current, the electrical current is proportional to the intensity of the current is proportional to the amplitude of the light. Brighter light, in other words, is going to cause more electrons to get knocked off. I think that's probably the nicest way to say it. Anyway, around the end of the 19th century, classical electromagnetic wave theory was saying this. They thought of light waves as being like water waves. And we've talked previously about the fact that it was around this time, the Michelson-Morley experiment, people were talking about whether light waves needed a medium or not. And of course, we came down to the conclusion that they do not need a medium. So they have some similarities, but they're not the same as water waves. But these waves' intensity or energy was proportional to how many photons were striking the surface per second. And so I've got some cartoons here. It turns out that if I have one flashlight shining light on a piece of potassium, that's an alkali metal, then it's going to knock off electrons. But if I have two flashlights, that's more intensity, more energy, then that's more photons, and it's going to knock off more electrons. I had to look hard to find a cartoon that would show this. I didn't feel like drawing it myself. Does the cartoon make sense to you guys? More light, more photons getting knocked off. Now, here's the thing, though. We've got potassium here. I labeled it so that it would match over here. Potassium metal undergoes photoemission. That is the ejection of those electrons, that photoemission, with blue light. So these guys could be blue flashlights. It would knock off electrons. They could be green flashlights. It would knock off electrons. But it turns out that if I use red flashlights, no electrons get knocked off. And at the time, this was a little bit of a concern. They're like, well, if we just make it be brighter, shouldn't that be more energy? More flashlights for everybody, right? Agreed? Well, remember what I said earlier. Electromagnetic radiation is higher energy when the frequency of the light is higher, right? And so if I want to use light to knock off electrons, I can't use low frequency radiation because that means that the individual photons are low energy. And when you bathe something in light, you're actually shooting individual or we can think of it as individual nuggets of energy that we call photons. And if each one of those nuggets isn't energetic enough, it won't knock off an electron.